And 5% I get for participation. In general, unless I really feel like you are disengaged, I usually give full credit for participation. Although I may change my mind at any time about that too. So, but in general, you participate, you're going to get that percentage. It's almost like a little bit of freebie. So that quiz is going to be your first little stressor, especially if you feel like chemistry is not your thing. But that's going to be, unless I'm still looking. I'm not going to be here. I'm going to be in Seattle, but I'm still looking for somebody to proctor this. I'm pretty sure I'll find someone, probably Dr. Self. So that will probably be on the 15th, and then you'll have 2 other exams. What I really want you to take away from this schedule is how it works when it comes to scheduling. This outline is a proposed outline for the semester. Things sometimes change. If something changes, I change it on the NAP calendar. You need to treat the NAP calendar, the one you can get, I suggest you subscribe to it. But if you don't, you can still go to the web link to get to it. That calendar is what we all update. Now, some faculty might change this as well or whatever if they're going to make a change. I generally do not after the semester starts. So if I'm going to have to, let's say I find out that I have nobody to do that quiz on the 15th, whatever I come up with when it's going to be, I'll send an email or an announcement, but I won't change it on here. And invariably, something I'd end up changing on here later this semester, someone would say, well, the outline says blank. It doesn't matter what the outline says after this, but the NAP calendar should reflect this. Okay, so if you look on the NAP calendar, you should see General Organic Quiz on the 15th. And that's what I will change from here on out when there is a change to the plan. I also want to point out this DVD. We used to be given a book with this DVD for every student by Baxter Corporation every year. Now we only have select copies. I have one. Dr. Self has a few. I gave him most of mine because this DVD is actually more beneficial for the pharmacology course than the chemistry and physics, and up until this year, I taught both courses. Now I course coordinate this course, and I will be doing some lectures for the pharmacology. So my point being, he has copies. You're going to have to share them and return them. There's 2 DVDs. I highly recommend you watch the first one. The second one is a plus minus. Basically, it's this guy, Dr. Eager, who is like an inhaled anesthetic guru. And he was paid by Baxter, and back when it was made, Baxter only made desflurane. And you'll see the bias. There's a little bit of bias in the whole thing about desflurane, the value of desflurane, although I think it has value. But he gets into all the pharmacokinetics and all the uptake and distribution, and it's really good stuff. Another thing that I found very interesting about the video is basically a video of him teaching. Like students, and these are students and residents, I don't know, maybe, I can't remember if it's students or residents, but before they take their boards. So these are people who have been doing anesthesia, and it's amazing to me, especially if you watch it, note how much they don't know. Like, they've already gone through all the coursework, and he's asking them questions, and they're clueless. And just remember, as you sit there, go, man, they don't know anything, and they've already been through all the coursework. Don't let that be you. I'm dead serious. Don't let that be you, because if you don't keep reviewing the stuff that you learn through this program, and just go back, and I mean, some people have really good systems where they do a lecture a week, you know, or something like that, you know, we're talking about a year from now, and they just go back and they review, just not because they have anything to do with any of the topic they're reading, but they just continually review. They're the ones that usually hold on to all this stuff, especially stuff that you don't use in clinical. Because really, when you get into clinical, a lot of the stuff that you learn in this class, a lot of the stuff you learn, like from that DVD, it's not extremely practically relevant in the clinical setting. But it is for boards, and it is for our expectations of your knowledge. So make sure you get that DVD watched. I highly recommend that you have that DVD watched before your first pharmacology exam on inhaled anesthetics. Because if he caters his exams anything to what I did, it's a valuable DVD to watch before. Okay, so so you won't have class that day. So I'm just kind of saying that's your independent study. Doesn't mean you have to watch it by the 8th. That's awfully early to watch it. You really just need to have it watched before that exam. You follow? As a matter of fact, the 8th might be a little bit premature because you're going to turn around on the 29th of September, have a lecture from Dr. Welliver. Dr. Welliver is one of my favorite professors of all time. He taught me. You will see in the chemistry and physics stuff a lot of his hand on what I teach you. And because he taught me pharmacology and chemistry and physics. And he is now faculty at Texas Christian University. And he lives in Yulee, Florida, not too far from Dr. McDonough. I'm trying to remember if he was at the welcome party. I think he was. He was at the welcome party. So many of you may have met him. But he does some guest lectures, and basically when he went on to TCU, I kind of pulled him back for the stuff that I thought, well, there's one lecture in the spring that is just like, no, really, I don't want to do it. Will you please do it? But the reason why he does the lectures this semester, and I know Dr. Self has secured him for the uptake and distribution lecture, is because he is absolutely excellent at teaching it. And so that's going to be a big day for y'all, the 29th of September. So that's where you'll have the chemistry and inhalation agents, but you'll also do a lecture on uptake and distribution for your pharm class. And that is the one drug that you're going to give that how it works, how it gets into the body, how it gets to the brain, how it gets out of the body, and the pharmacokinetics of it is so counterintuitive to anything you understand about drugs. Because all the drugs we think about injections, or we think about oral intake and then absorption. It's different. It's just different. And things like, why would someone with lower cardiac output actually be able to go to sleep faster? I don't get it. I don't understand. That's what you're going to be as you're studying until Dr. Welliver arrives. And that's when a lot of people have aha moments. So, yeah.
For the DVD, you said you have one on that class day. We have to already be here in the morning and in the afternoon. So is it possible that we could watch it in here as a class?
Which day are you talking about?
On the 9th, or 8th, 9th.
It's a pretty long DVD. I think it's a couple hours at least. Okay. I think the first DVD is 6 lectures. So it's at least 4 hours of watching, I'm pretty sure. It felt like that when I watched it. Maybe it's not as long as I think. As far as that goes, though, do we have media to play DVD? Here? Oh, I guess somebody could put it in their laptop and stream it. There will be limited faculty here as far as support for that. We can look into that if y'all want to. If y'all want to do that. Sure. I still think though the 8th might be a little early. That's my one thing. Like if you watch it then, and then you're going to be learning so much that I would recommend the week prior to the 29th is the ideal time to be watching this DVD. So that's my one reservation as far as the timing of it. I mean, I have it on the schedule there just because that's the date I won't be here. So like, but if I were going to time it more appropriately, at least the 15th is when I would be watching it. By the 8th, you're going to be thinking about other things, like regular pharmacokinetics that Dr. McDonough teaches, or the stuff that I know he's going to give you a video, because just the timing is I can't do a live lecture where I come in and I break down things like volume and distribution and elimination half-times and half-lives and all this clearance and all these concepts and all stuff that some faculty would think you should just learn and know. And I just like to kind of break it down for you guys. So that will be provided for you via video. And those are the things that you're going to be really focused on the next couple of weeks. So, all right. So then we'll get, so you'll see this exam 1. So the way I do exams, they are cumulative and not. The last exam of every semester is absolutely cumulative, 100% cumulative. You will have questions that are basic general organic chemistry questions, just like you do on this quiz coming up in a couple weeks, as well as the new stuff. in between exams, like exam 1 in this case, will only be cumulative in where it applies to the new material. So like in this exam 1 here, I'll have questions about chemistry of inhalation agents in there. Well, there's some stuff about ethers and that kind of thing, which is also covered in the next 2 weeks here. So yes, it's cumulative and of that, but it won't be like I'll just pull a question that's completely unrelated to this topic, and this topic onto this exam. Okay? So generally, you don't have to sit there and go, okay, let me review my chemistry, general and organic chemistry in general, only as it applies to the new material. Final exam, everything's new. Okay? Okay. Any other questions before we get on it today? Oh yeah, by the way, I'm thinking December 1st, just because looking at the calendar, let's do it real quick. So here I have subscribed to a whole bunch of calendars, but just to make it nice and easy, let's take a lot of them off so we can see the NAP calendar. Wow, I have a lot of subscriptions. Oh, I got some that aren't working. Why is that? I'll have to figure that out later. Okay. Okay, that's pretty much most of them. All right, so this is pretty much the EBP calendar subscribed onto my computer. And if we jump to December, on the 1st, I see you have exam 3 for principles. You have me putting in a question mark there. Nothing for farm as of right now, or it's just not updated. I'm not sure which. And then on the 8th, you do have exam 3 for farm. So it's kind of, we'll just see. I can kind of go either way with it, and you know, I'll just look to balance the 2 weeks out. Okay, so we'll see. So it could be either of those weeks. Chances are, if it's the 8th, I'll either cancel the 1st, or I'll have a little review something or catch up on something. Because on the 1st, there won't be class on the 8th. So, okay. Okay. Let us. All right. So, general chemistry. This course, when I took over it years ago, was very different than the course I took when I was at FIU and took chemistry. Now, I did say that Dr. Weller taught me chemistry and physics. Technically, actually, he taught me physics. And another thing I didn't really mention is we have chemistry and physics 1 and chemistry and physics 2. Chemistry and physics 1 is this semester, chemistry and physics 2 is next semester. Reality is, you could almost call this course chemistry, next course physics. And it's just because this one is heavy chemistry focused, next semester is heavy physics. There's a little bit of blending, of course that's always true with chemistry and physics. So he actually taught me my physics course. He did not teach me my chemistry course, as I badmouthed my chemistry course when I was in FIU, because my chemistry course, we used a general chemistry book that had nothing to do with anesthesia, and that you still have that problem to this day, except that anything in that book we had to learn. So we were learning, and we were doing delta H calculations. Anybody even know what that is? Like enthalpy calculations? Nobody? I don't have my chemistry guru in the room. Or you've learned not to admit it.
Is it like heat transfer? Is that what delta H is?
Yeah, like the delta H, and you'd have to, you know, when you're looking at exothermic and endothermic reactions, you'd actually have to do a calculation to determine the amount of heat produced or absorbed. We had to do all that stuff. Yeah. We had to balance these massive chemical equations, and I mean, all sorts of stuff that I'm like sitting there going, me with a strong chemistry background, going, I'm 99% sure we won't ever need to do this ever again and past this moment, and that was absolutely true. So then this course was taken over and taught by Dr. Welliver here before me, and he had already really started to cater to anesthesia. And then when I took over, I kind of took it a step further. So this is a very applied course. in some ways, this course is easier than any chemistry course you're ever going to take. Now, I don't want you to think it's going to be therefore easy, especially if chemistry is hard for you. Some people do find this course very difficult, okay? But, and other people, especially if they have strong chemistry background, they rock this course. So, but the point being, I try to only focus on the things I really think you need to know. The concepts, things that I feel like are applicable. And even then, there's a couple things that I teach, like today especially, where I'm like, you really don't need to know this, except there's like maybe a thread of need to know. So I have it in there, but I mean, I have really tried to turn this into a true applied chemistry course. So what you're learning in general is truly need to know stuff, and you will still sometimes feel like, do I really need to know this? And the answer is, I say you do, so you do. But in general, how you might feel right about now is maybe something like this, that you're about to dive into a pool with no water in it. And, I don't know, I actually put these pictures in my slides a couple years ago when this was the very first day of the very first class for everybody. You didn't have 2 semesters prior to this to already feel like some of you already, I've already felt that way for 8 months now, Dr. Short. I mean, some of you might have felt like, I still feel like I'm falling, and the pool's about to, so, but anyways, is this how you feel? Maybe. You might also feel like this is our plan for you, that we're just, I'm going to get you, or whatever, and that is absolutely not the case. I mean, I can promise you this faculty wants you to succeed, and we're not going to hold your hand and let you be dangerous. We're not going to graduate you when you don't deserve it or when you really shouldn't. But we want you to succeed, every one of you, So, and I can also promise that this has never happened. No one has ever studied hard enough that they spontaneously combust. And if so, I will make the next class do delta H calculations. So, but anyways, but do remember that studying is like water. You actually put water in the pool. As you feel like you're diving in that pool and there's no water in it. If there's water in it, you're safe. The more you study and the more you apply yourself, the more you're making it safe. Okay? And so just keep that in mind, all right? Okay, little pep talk, time to move on. All right, one of my least favorite applicable things, but I still make you learn it, is significant digits. So when we say a digit is significant, what we're immediately saying is the value of that digit means something to me. For example, if I say an elephant weighs, what about 10,000 pounds? I don't know. How much does an elephant weigh? Probably. Let's say 10,000 pounds. If I say they weigh 10,000 pounds, does that mean exactly 10,000 pounds? What if it's 10,100? Would I bother to say that? What if it's 10,000 and 1 ounce? 10,000 pounds and 1 ounce. Like, how significant are all those zeros that I said when I said 10,000? How specific is my scale? Because it may be a scale that is only to the nearest 100 pounds, I mean, I promise you, a scale that weighs a semi-truck can't measure to the nearest ounce. And it certainly can't measure the nearest gram, nanogram, or anything like that. So when we say that truck weighs 50 tons, it could be 50 tons plus an extra couple 100 pounds for all we know, because that scale is that off. And I promise you, every time I don't like what I see on the scale, I say, yeah, these are not significant digits. So how do you determine what a significant digit is? And where this becomes very applicable is when you're doing calculations in chemistry and physics. And when you're doing a calculation, you don't want to get your answer to have some significance that the data you had to begin with did not have. So anything non-zero is considered significant. So for example, the number 123, all those numbers are significant. That means that unit, let's say we're talking about grams, that scale was specific enough that it could tell you there was 123 grams there. In between, it's a significant digit. Leading zeros are not significant. So like 0.123 or 0.000123, those zeros do not count. So that particular example, both of those only have 3 significant digits. And then trailing zeros in a number containing a decimal point are significant. For example, 1.230. The fact that you have this 0 here tells you that that scale was so specific, it could measure to the nearest thousandth of a, let's say, gram, which would be a what? Nanogram, milligram, microgram?
Milligram.
You do need to know those like prefixes. That's just kind of, I think that's kind of general nursing knowledge, but you do need to know that. So how many significant factors does each of these have? So everybody look at them for a minute, and then we'll go over them. Give you a chance. Bless you.
Can you explain further? The only one I'm having a problem with is, when you've got a decimal and then a 0, 0, why are those 2 zeros after the decimal not significant? Because if you're doing drug calculations, you would want those zeros in your calculation.
They're just placeholders, and that's the best answer I got for you. I just know that's what it is. Okay. I didn't make the rules. I can explain some of it. I can't. That one I have a little harder time explaining, but we'll just say it is what it is. It's not that important anyways. Beyond today or your exam. Okay. So first one. 3.
Yeah.
Second one.
4.
And the last one. 5. That last 0 does count. Good. All right. What about the last one there? 54,220 kilograms. Just 4. That 0 doesn't count. Okay. All right. This is a little bit more important. This is quite a bit more important. Scientific notation. Scientific notation is a great tool that we use to simplify a really big or really, really small number. So, like, for example, if I give you this number 0.00006, we could just instead say 6 times 10 to the negative 6. Or if the second one, 0.0000832, we can write this, 8.32. Oh, yeah. I encountered this one other time. The laser pointer doesn't really work on these LED screens. There's some science there I need to learn about. So, all right. So, there's not too many times we use scientific notation. But can anybody think of, especially if you did any preparation, like you looked at these slides ahead of time or whatever, where we definitely use it?
Oh, yeah.
Avogadro's number. Anybody know what it is? This is Avogadro's number. Okay? Now, can you imagine writing this thing out every time we wanted to deal with it? By the way, let's go ahead and see how it's done. And this is how you convert from scientific notation to non-scientific notation. You start with the first part, or sorry, I know it was 0.23, but that's probably wrong. Anyways, you start with this. You're going to move this decimal. You're going to move it 23 times. How do you know which way to move it? Well, if you're going from scientific notation to normal, if it's, sorry, that's wrong. It's positive, you're going to be, it's a big number. 10 to the 23rd is a huge number, so you're going to go to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 21, 22, 23. There's your decimal. All these are zeros. There's no more decimal here. That's the number. It's massive. Okay? Can you imagine if I made you write that out? You'd probably get it wrong just because you accidentally leave a 0 out, you know. So 6.022 times 10 to the 23rd. If, I should have left that there. If you have that number, and you want to convert it back, here's the rule. In scientific notation, you must have a non-zero to the left and only one digit to the left of the decimal. Okay? So you're going to move that decimal until that is true. Okay? So right now I have more than one digit to the left of the 0. Okay? So I'm going to start moving it, and let's just pretend I moved it 20, at this time 23, 22, 20. I moved it now 21 times. I still don't have only one digit to the left. 22 times, 23 times. Oh, I've reached to where I only have one digit to the left of my decimal. I stop. Okay? At this point I stop, and I then ask myself how many times did I move the decimal? 23 times, so I'm going to say 6.022 times 10 to the, how many times did I move it? 23. Now, if you were dealing with a small number, something very, very small, like, anyway, I'll just come up with a number. So we have a number 0.000000112, okay? And we want to convert that to scientific notation, you're going to do the same thing. Whenever you're converting scientific notation, you always move the decimal until you have only one digit to the left, not a 0. Because right now, we have one digit to the left, but it's a 0. So we're not good. All right? So 1, 2, 3, 4, 5, 6 times. Now we have a 1 to the left of the 0, so we stop. 1.12 times 10. How many times do we move it? 6 times. Is it a tiny number? Yes. Negative. Okay? And it's the same concept going back. 1.12. We need to move this. 2, 3, 4, 5, 6. Decimal is here. 0, 0, 0, 0, 0. And you can add a leading 0 or not. I don't care. You know. So that is how that works. I think that's all I have to say about that. Okay. So this also very important. There are many ways to measure temperature. We'll have a whole lecture next spring about temperature and hypothermia and all of that. However, in the wonderful wisdom of healthcare, although when I'm being sarcastic about the wisdom, I might just say medical care, which, by the way, just really watch the habit of what you ever say. You do medicine? I've always been interested in medicine. No. Well, I mean, maybe that's true, but you chose a different path. It's healthcare, right? If you want to be universal, just say healthcare. You can say nursing, but just it's a buzzword to try to get out of your vocabulary. Just saying. But anyway, so I'm gonna blame healthcare on the decision that we intermingle Fahrenheit and Celsius when taking care of the same patient. And where I work at UF Health, we do that every case. They take a temperature of the patient in pre-op holding in Fahrenheit. We monitor their temperature in the OR in Celsius because we're smart and we know the better one to use. And then we take them to PACU and we measure their temperature in Fahrenheit. Real smart. So yeah, that makes a lot of sense. But the reality is you do need to know how to convert from one to the other. And yes, I want you to be able to do that without any special app. Now you may use a calculator, and when you get to your chemistry quiz with me and all your other exams with me, you are welcome to use a calculator. I have no problem with calculators. They help eliminate med errors. But you cannot use a smart calculator that will do it for you. You can't use an app. You can't use your phone. My rule is a regular scientific calculator is fine, or a simple app on your laptop is fine as well. A simple calculator app, okay? Not something that's designed to do this. So you're going to learn how to convert from Celsius to Fahrenheit and the other way around. Let's take something we know very well. What is normal body temperature in Celsius? 37 degrees Celsius, right? What is it in Fahrenheit? 98.6, which, you know, there's like a rule, like, it can never say 98.6, right? I mean, has anybody ever seen a 98.6 ever? You know, it's always lower or higher, right? So, anyways, so we're going to convert this. So, I have little ways of doing things that I think is easy, because there's a formula, but I don't even have the formula memorized. I just know a few numbers. One of the numbers is a fraction. 9 over 5, or the inverse of that, 5 over 9. Remember that one? And remember the number 32. Remember those two numbers. You have to memorize those numbers. Okay? And then there's a rule you need to memorize. You never, because the 32 is always plus, or you're either adding or subtracting the 32, and the fraction you're always multiplying it. So you never multiply the fraction against the Fahrenheit number, ever, ever, okay? So these are the rules. So here we have 37 degrees. We're going to have to either add or subtract 32 at some point. We're going to have to either multiply by 9 over 5 or 5 over 9 at some point. Which one do we do first? Well, we have the Celsius, so let's do our fraction first, because we never do it to the Fahrenheit. What's always the bigger number, Fahrenheit or Celsius?
Fahrenheit.
So if we multiply this by 5 over 9, will we get a bigger number? No. So we must have to multiply by 9 over 5. This is how I remember these things, right? So I say 37 times 9 over 5. You may use a calculator.
66.6.
What?
66.6.
66.6. Now we have to do this other part. We're either going to add 32 to this number, or we're going to subtract. Are we trying to get a bigger number here?
Yeah.
Yes, because we anticipate going to Fahrenheit's bigger. So we're going to add 32 to it, and what do we get? 98.6. That works. Okay? Let's go the other way. Let's say they say the patient's 97 degrees. Well, I'm in recovery. They say they were 97, and I know I saw that they were 37.6 bladder temperature before we left the OR. Are those the same temperature? I don't know. Doesn't sound right. As a matter of fact, one sounds below normal, and the other one sounds higher than normal. Let me convert it and see for myself. So let's do that. We're in degrees Fahrenheit here. So we're either going to do our fraction first or our addition and subtraction first. We never do the fraction against the Fahrenheit number. So we need to do the 32 first, right?
Right.
Are we trying to get a smaller number or a bigger number? Smaller. Are we going to multiply by 9 over 5 or 5 over 9? Which is?
53.88.
Okay, yep. That sounds maybe possible. Is that what it is?
That's what I got.
53.88? Okay. Now we got to do our 32 thing. Are we trying to get a smaller number or a bigger number? Smaller number? Something's fishy here. Did anybody else do this calculation?
Sorry.
Yeah, because you don't do the 32 first.
Yeah.
You
Look
just
what I just did.
Yeah.
I'm sorry.
Yeah,
I had 1 hour
just-
sleep last night. I was an OB.
Never do math.
I'm on vapors here. Okay. Yeah, OB sucks. Anyways, so yeah, thank you for fixing me. Good. So this is what happens when you do it in the wrong order. So 97, so we're going to subtract 32 or add 32?
Subtract.
Subtract, yeah.
Thank you.
Right.
And now what do we have? Well, that's easy math, right? 65, right? Now, are we going to multiply by 5 over 9 or 9 over 5?
Probably 5 over 9.
Yeah, 5 over 9. 36.1 degrees
That's
Celsius. And they were 37.3 in the OR. They lost 1.5 degrees of Celsius on the way. Or maybe one is a core temperature measurement and the other one's a peripheral temperature measurement, which can be a couple degrees different sometimes. So, all right, there you go. Now, let me go to Kelvin. Kelvin is a temperature that is more like a measurement of, it's the best temperature that really truly measures state of the thermal state of something. To the point where if there is zero thermal anything, if there's zero heat in something, none at all, it's 0 Kelvin. 0 Kelvin is basically unattainable. It's called absolute zero, okay? And it is an absolutely unattainable number. We don't achieve anything in the world here at absolute zero that I know of. Maybe some scientist has done it and it's a secret because it's a weapon or something. I don't know, but that'd be like a phrase weapon. But anyways, so I just had like Game of Thrones thoughts. But anyways, so it's truly a measured thermal state, because when we say something's 0 degrees Celsius, there's still heat there. I know hard to understand it that way, but really there's still the presence of something warm. It's just colder than what we're feeling. But let's just say you really liked it at negative 50 degrees. That was what you're used to it being. You would think 0 degrees Celsius is very, very warm. So, I mean, if you want to think about it like this, let's say you're in Minnesota during a wicked nor'easter in the middle of the winter, and it's negative 30 degrees out, and all of a sudden, next thing you know, it's 0 degrees Celsius out, and you go, it warmed up.
Put on your shorts.
You know what I mean? So, and some of you can probably relate to that, right? So, 0 degrees Celsius, there's still heat there. But 0 degrees Kelvin, there's none. And the conversion from Celsius to Kelvin is this number, 273.15. So if you are converting from Celsius to Kelvin, you basically add 273.15 degrees. Which means when you are at freezing temperature of water, we actually have 273.15 degrees of heat. From the point of 0, nothing. Absolutely nothing. So, which is absolute 0. So the reason we never deal with Kelvin in the healthcare field, okay? But when it comes to certain calculations, especially with like we'll do gas calculations in the spring, all those formulas are based on Kelvin. So you have to be able to learn to convert to Kelvin. And so this is something you must be able to do. You never do math when it involves a Kelvin with Fahrenheit. You never add something to Fahrenheit or subtract something from Fahrenheit when you're dealing with Kelvin. You have to convert to, let's say you're starting with Fahrenheit, you have to convert to Celsius first, then to Kelvin. Same thing, if you're going from Kelvin to Fahrenheit, you have to go from Kelvin to Celsius, then Celsius to Fahrenheit. There's no direct, well, there probably is a formula, but it involves doing that first. So just remember that. And you think I want to ask you just to convert from Celsius to Fahrenheit on an exam? Maybe. But I'm probably more likely to ask you to go all the way with it, one way or the other. Okay? There's some sample problems there. All right. Temperature will pop up a couple times throughout the program, and that need to be able to do that, especially gas laws, probably sometime early in the spring. Matter. I don't know why. This one trips 20% of the students up. I don't get it. And I'm not saying they're dumb. I'm just saying it's just one of those things where some people totally understand it and some people don't. But matter can exist in two forms. It can either be heterogeneous, which means that there's more than one phase or an uneven distribution of substances, or it can be homogeneous, which means it has a single phase or even distribution of substances. So, I'm swatting at air right now. Do you see, like, anything in this air, like, I mean, maybe you do see things, you know. But, I mean, do you really see anything different, like that spot of air versus that spot of air versus that spot of air? Does it all look the same to you? It all feels the same, right? And you can all do that too if you want. And then we'll put the camera on you guys. So, homogeneous. There's only one phase here. There's an even distribution of the substances in it. What substances are we talking about? What molecules? Oxygen, nitrogen, carbon dioxide, I don't know, cyanide, some really bad stuff too. Depends on how much you read those Facebook posts. you know? But anyways, did you know you're breathing today? No, there's other stuff, but you know, in general, those are the main three, especially nitrogen and then oxygen, right? So it is a mixture of things, which is now this part of it. It is a mixture, but it is homogeneous. Now, when you look at any of the retention ponds in the middle of the summer at the crack of dawn, what do you see right above the water? Little pretty clouds. You know what I'm talking about? You see it like every day in the summer, the morning, you see that steam coming off the retention ponds. That vapor is water, right? And once it is fully, there's also water in this, right? There's water here as well. There's other stuff than just oxygen and nitrogen. But once it becomes fully evaporated in the air, it is homogeneous. It is a mixture. But when you have that state of liquid, which is the vapor, the condensation part of the vapor, and the non-condensated part, we actually have a heterogeneous mixture. Okay? So that, you know, that's just one of many examples. So let's take ice. Okay? Let's just pretend for a minute that you have ice that's made from distilled water. And when I say distilled, that means they did this whole process where they evaporate it away and then recondense it, so all the other materials that were in the water are gone. Okay, so we're talking about pure H2O, only H2O in there. So we took this distilled water. First of all, it's water, it's only liquid phase. Is that a homogeneous substance or a heterogeneous? Homogeneous. But then we froze some of it. Let's say we froze all of it. Homogeneous or heterogeneous? Homogeneous. But then we put that block of pure distilled water in some more pure distilled liquid water. Heterogeneous, pure substance, because it's only H2O. Now, any water you drink out of a water bottle, for the most part, unless it's truly distilled, and certainly out of the tap, may be homogeneous, but it is certainly a mixture. Okay? So once something else, a different matter, not a state of matter, but a different substance is in it, it is no longer a pure substance, it is a mixture. Sugar. Sugar is sucrose. So if it's pure sugar, that makes it a pure substance, but it's also homogeneous. It's only in the crystalline form. The only way you can make it heterogeneous is to mix it in where some of it has dissolved and some of it is not. In that process, you know, like Southern iced tea, when you add the sugar after it's iced, you know. No? Not a good idea. Anyways, I keep adding more. So, all right, that one don't get, huh? Okay, fine. So anyways, peanut butter has oil, it has all sorts of stuff, so it's a mixture. Even whether it's crunchy or creamy, it's a mixture. Sorry, it is. And it's heterogeneous because there's still like little substances. But to make it real simple, if you want to really be sure, I'll say crunchy peanut butter. Heterogeneous or homogeneous? Heterogeneous. Okay. Gasoline. Did you know gasoline is not all one compound? It's a mixture of many different alkanes and some saturated, unsaturated, and just a bunch of different stuff. They even add some phenols in it and all that kind of stuff. It's actually a mixture. Even though it's homogeneous when we see it, it looks like one thing. It's actually a mixture of many things. Unless you're talking about like a pure natural gas, that might be a highly selective thing. Like propane, for example, is propane, and propane actually is a particular compound, and you'll have to be able to actually recognize that by the end of next week. If I told you propane, you'd actually draw it out for me. So, okay, moving on. So, periodic table. So, if you haven't figured out yet, I do carry a nerd card. I am certifiably a nerd. And if you really do enjoy me and all my jokes, then I have news for you. You're in my club. So just let you know. So and male and female alike, I've had them join me throughout the years, and the thing is, I don't try to point that out too much. You know, I try to let you just kind of figure that out on your own, but I'm just letting you know. But anyways, I like the periodic table of the elements. It's just always fascinated me. I mean, yes?
How do you feel about shoes?
There you go.
Oh my gosh. Now wait, you both have the same shoes
You bought them together.
for this class?
Of course.
That's fantastic. I love those.
So unfortunately, we are part of the nerd club.
Now, I have to tell you something though. You're off limits on exam day.
Dang it!
I'm on you guys. So, but very, very nice. I think that's awesome. Yeah. So, where did you get them?
Get him a bag.
Where do you get Toms? You guys get Toms?
Yeah.
I told you I'm wearing
They
this.
should now.
So, okay, all right. Do they have guy versions?
Yeah.
All right, so rows in the periodic table are called periods, columns in the periodic table are called groups. Elements in a given group in the periodic table share many similar chemical and physical properties, and this is the kind of stuff I really like about it. You can look at the periodic table and you can tell if you know a lot about fluorine, you now know a lot about everything in that column. Stuff like that, it's cool stuff. So, but anyway, so these are called groups. These are called periods. I usually just call them rows and columns, make it easy on everybody. That's just the way I think of it. And there's a whole lot of elements in the middle here that I don't worry much about. Okay, there's a few spot ones, in there somewhere, like gold matters to me. I don't know, but, not really for you guys, but for this course. But anyways, there's a couple in here that are iron, for example, is very important. But pretty much the higher you are on this table and the more you're on each side of the table, it's applicable to us. All right. And the main reason why is things that are on the sides, with the exception of this column, are extremely reactive. And the things in the middle just don't care. That's one of the main reasons. So, all right. You need to know some names for some of these columns, these groups. Like, for example, anybody know the name of the 1A group, this group here? I'll never call it 1A in the exam. Anybody know? Starts with an A. Alkali metals. Yeah. Less important to know, but I'm like, I don't know. You need to know it. The second one? Alkaline earth metals. Very good. What is this last column here? Noble gases. How about this one? The second to last one. Halogens. Definitely need to know that name. Definitely need to know that name. And this one is halogens. You don't need to know it. It sounds a lot like halogens. And they behave a lot like halogens in a way. So, let's talk about what's on that periodic table, these numbers. So when you're looking at silver is Ag. There's a number up here on the top, a number down here on the bottom. Some periodic tables have even a little bit more information, but these are the main numbers of interest. So the top number here is the atomic number. And they go in order, 1, 2, 3, 4, 5, 6, 7, 8, going along from one end of period to another and then down to the next row. And then the name here, the elemental symbol, and then the atomic mass, which is in grams per mole. We'll get to that. But think of it just for now as grams, okay? No pounds or ounces here. We're going to stick with numbers that make sense to use. And so that's this part right here. What else can you tell? Anybody know anything? The 47 automatically tells you the number of what? Protons in an element. That's right. Does it tell you the number of neutrons? Does it tell you the number of electrons? If it's neutral. Yes, good. So protons and electrons, it pretty much, for the simplicity, that's what it tells you. The neutrons is a wild card. Okay. All right, good. So here's your alkali is actually more correct than alkaline for the first one. A-L-K-L-A-L-I. But anyways, all right. Now, another thing you need to know is If you cut a line right here, everything here is considered, with the exception of hydrogen, considered a metal. And everything over here is considered a non-metal. Now, if you want to get really technical, right here we call these metalloids. But what's important about that is generally metals like to react with non-metals. It's just they enjoy that. They enjoy hanging out, getting together, or beating each other up, one or the other. So for nonmetals, when they're observed at, physical properties of nonmetals are observed at room temperature. Examples include like chlorine gas, bromine gas, iodine, bromine liquid, iodine solid. They are generally poor conductors of heat and electricity. Many exist as diatomic molecules. Anybody think of another one?
Oxygen.
Oxygen. That's right. A diatomic molecule. They gain electrons when reacting with metals, but will share when reacting with each other. So when nonmetals get together and they form a bond and they get a little like kumbaya going on, they're very sharing. When they react with a metal, they're very taking. They're the bully. So you can also think of like when you're dealing with metals and nonmetals. Metals are the pacifists. Here, take my electron. It's okay. You can have it. And the nonmetals are the bully. Yeah, you darn right I'm taking your electron. You're gonna like it. So, all right. There's your metalloids. Not really very relevant for us. Don't worry about that. So, another thing very important to make a distinction of. Element. Element is a pure substance that contains only one type of atom. So, carbon dioxide. Element?
No.
No. Each element has an identical number of protons in their nucleus, which cannot be reduced to a simpler substance. There are 117 elements on the periodic table. So, O2, the letter O, a single one of those, is that an element?
Yes.
Yes. What about O2?
No.
Yes, because it's only that one type of atom. Okay? And this is where you really get the distinction between an element and a compound. When we talk about a compound, now we get more than one type of atom. Like CO2. You have carbon, you have oxygen. They're all bonded together, and now we can't call that an element anymore. Okay? An atom, a single O, is that an atom? Yes. O2, is that an atom? No. Because now you have two atoms. Okay? All right. Molecule. Now, a molecule can be like a compound, or a molecule could be like O2. Okay? Now we're dealing with something that is more than one atom together. A little technical, but there you go. So, generally, what we learn about is any atom has a nucleus, and then it has its orbital electrons. The nucleus has protons and neutrons in it. The protons carry a positive charge, the neutrons carry no charge, and then the orbiting electrons carry a negative charge. Okay? So if you were looking at carbon, you would see a 6 above the C. That means its atomic number is 6. How many protons? How many electrons? Let's just, neutral for now, okay? On the bottom, you would see a number like 12.0 something. Like 12 point a little bit. That's the mass number. That means that 1 mole of carbon has a mass of about 12 grams. Okay? So, and 1 mole is, by the way, Avogadro's number. So 6.022 times 10 to the 23rd C's weighs 12 grams, which actually is something you can feel in your hand. So, all right. Now, an isotope is an atom with the same number of protons, but having more or less neutrons than another. Another thing let me back up a second. Electrons carry almost no mass at all. They are so light that we don't really bother to measure them or try to weigh them or give them credit. when it comes to mass. They actually do, when you get the bigger molecules, they have like 100 electrons, it does contribute to the mass. But when you're dealing with the smaller ones, almost nothing. Okay? And to keep everything simple, although it's not exactly a gram per mole, a neutron has a mass of a gram per mole. A proton has a mass of a gram per mole. So when you talk about the three things that compose the carbon, your neutrons, your protons, and your electrons, the two things that are actually making up the mass of that carbon are protons and neutrons. And in this case, the atomic number being 6, meaning 6 protons, if I tell you that the mass of that carbon is 12 grams per mole, how many neutrons are in this carbon? 6. Now what if I told you it had an atomic mass of 14? There would be 8 neutrons. Okay? So look at hydrogen here. So the hydrogen that we're mostly familiar with, the hydrogen that is mostly existing in this world, is protium, which is basically exists of 1 proton. And a lot of times sometimes that electron is being shared, sometimes it's being given away. That's another topic. But as far as the nucleus, there's only 1 proton and 0 neutrons. And if you look on a periodic table of the elements, the atomic mass for hydrogen is like 1.001, something like that. Okay? And no, you don't have to know that. All right? You do need to know it's around 1, right? Okay, but most of them I don't expect you to know. There's a few, but most of them I don't expect you to know the mass of them. But you can have an isotope of hydrogen where it still has 1 proton, but it actually has a neutron. Weighs twice as much. And then you have obese hydrogen, which has 2 neutrons and 1 proton, and it weighs 3 times as much as protium, the hydrogen we're familiar with. Okay? Both overweight deuterium and obese tritium are not so common, but these are what we call isotopes. So another example of isotopes would be what I was referring to, the carbon. Although not so common, there is an isotope of carbon that actually has 2 extra neutrons. And so therefore weighs more. Okay. Let's press a little longer before we take a break. This is when it gets really hairy for a few of you. Just telling you. This is good stuff, though. This is important stuff. Valence electrons. If I say sp orbitals or s orbitals or p orbitals or anything like that, did anybody just get like erectopili action there? Yeah, because you remember something about that. Yeah, you used to draw the circles and do the little or the x's or yeah. I don't make you do all that, but you need to understand the concept. You need to understand why it's relevant to all that we're doing. All right, so valence, think of it like this. Okay, you got your, let's say we're talking about potassium. Okay, all right. Potassium has its nucleus, and then think of it like, you got your troposphere, your stratosphere, your ionosphere. Some of you are like, what are you talking about? Layers of the atmosphere around the Earth, right? So you have like different layers of electron orbit. Okay, and they are defined by these rows. So first layer, second layer, third layer, entering a fourth layer for potassium. So there's like several, like onions or parfaits that have layers, right? I make a lot of movie references, and most of them I only get like 2 responses. Every now and then I get like none. But anyways, parfaits have layers. Thank you. So think of it like that. Well, only the outer layer, the absolute outer layer, do we care about. Because in the end, that 1 electron that's floating around for potassium, how do I know that? Because it's only got, once we get to here, we get noble, we're real good, we added 1 more. Only that 1 electron is going to be reactive. It's on the outside. Why would an electron from the 3rd layer in go reacting with another compound or another element, or another atom? So only the outer layer do we care about. We call those the valence electrons, the one on the outside. So as we move from left to right, we gain valence electrons. 1 valence, 2, 3, 4, 5, 6, 7, 8 valence electrons. We skip the Ds, although there's this SPD thing or whatever. Don't worry about it. You don't even have to worry about it. I haven't even explained it in years, so don't worry about it. But we kind of skip the ones in the center here, and we only deal with the ones that have the letter A, all these. And so one, like for potassium going on to this side, 1, calcium has 2. We don't deal with these. Gallium, I think, I don't know. You don't, some of these you don't have to know. Bromium has 7. Krypton has 8. An atom, and here's the key piece, an atom is so very happy when it has 8 or 0. On that outer shell, it becomes extremely stable, extremely happy when it has 0 or 8. Anything in between is unsettling to some degree. Now there are places where they're semi-happy, like if they have 2, they're way happier than if they have 1. If they have 6, they're kind of, okay. But once they get closer to one or the other, the closer they get to 0 or the closer they get to 8, the more irritated they are. The more they're, chlorine is extremely jealous of argon. I mean, he hates argon with a passion, like Cain and Abel here. Big time hatred here, all right? And so, argon's just sitting there, and chlorine's like, I'm just so close. So chlorine will do anything it can to be like argon. It'll kill, right? To be like argon. The higher you are on the list, also, the more volatile. So helium's very happy, neon's very happy, but fluorine is higher than chlorine on this list, and just as close, 1 away. So fluorine is more angry than chlorine is that it's not its brother, okay? So fluorine hates neon more than chlorine hates argon. And, iodine's kind of like, yeah, neon, they're more happy than I am, but I could kind of be like this too. Because they're way down on the list, right? They got lots of electrons around them, so that one more that they need way out there, oh yeah, that's right, I'm missing one. So that's the way you need to think of it. The higher on the list, and the more towards the end, but not on the end. Well, here, this is extremely volatile. They want to be here, okay? Noble gases. That's why they're called noble gases. They don't need anybody. They're good. All right? That's the way you need to think of it. All right? Now, the reason why these guys share with each other when they bond is because they both want. So when fluorine, let's say sulfur, gets around oxygen, for example, and sulfur says, hey, I want your electrons. And oxygen's like, no, I want yours. No, I want yours. No, I want yours. Well, okay, why don't we share? Whereas when oxygen gets around sodium or lithium or any of those, oxygen's like, I want yours. And lithium's like, here you go. So they'll just give it away. All right? So that's the big difference. That's why we say they share here, whereas they more give away when they're on each side. A perfect example of all examples that we know is this one right here, sodium, and this one right here, chloride. Sodium chloride. So when sodium gets around chlorine, they're good. They're like, hey man, chlorine's like, you're gonna give me my electron. And then chlorine's like, well, it's actually, sodium's like, it's actually mine, but yeah, you're right, it's yours. Go for it, take it. And then sodium's super happy, it gave away one, and chlorine is super happy because it now has. So sodium went from 1 to 0. And chlorine went from 7 to 8. Okay? So this explains a lot about the reactivity of substances. Electron negativity, there's also an electron positivity. There's a couple of different expressions, but I'm kind of focused on this one to keep it simple, is basically the ease at which neutral atoms will lose electrons to form positive ions. We'll get to ions. And that increases to the left and toward the bottom of the periodic table. So this is really how I like to think of it, though. The higher this number, the more it's actually going to be like wanting an electron. The more it wants one, and it certainly isn't going to give one away, right? So the one with the biggest number, what you know is it is the biggest, baddest bully in the entire periodic table to take electron. The ones with the smallest number are like the opposite. When they're getting down to like less than 1 or near 1, they're not a bully at all. They're going to give it away. That's the way to think of it. And you can see when you look at the color coding, as you move this way, they become more and more bullies. All right. There are some exceptions, there are a few that kind of mix in a little bit or whatever, but in general, that is the case. Okay. You notice even like this is a little weird. Krypton and xenon are actually a little bit more affinitive to electrons than you would think they would be. You would think they'd be like, no, don't give me any more. So, but generally that's your rule. You can also see there's a little bit of mixing around in here. Gold is actually highly electron negative, and it has to do with that SPD stuff and stuff I said I wasn't going to get into, so I won't. But it also has to do with like gold conducts electricity, which not for us, but interesting to me. Anyways, all right, got that? When we talk about ions, though, the way we define, the way like chemists kind of cut off and decide that the bond that's created is an ionic bond has everything to do with the difference between the two numbers. Like the more the gap is between two numbers of the two atoms coming together, the more we'll consider it an ionic bond where it was actually a giveaway as opposed to a share. So let me kind of jump ahead a second before I move on. We have a couple different kinds of bonds. The main ones we focus on by far are covalent and ionic. Covalent, like cooperation, valent electrons. Covalent are where electrons are shared. Ionic, complete giveaway, a complete take. So the bigger this gap, like this one right here, a gap of like 2.2, that's ionic. And there's actually an actual number like 1.7, 1.8, something like that. When the number's greater than that, we consider ionic. Don't worry about that. But anyways, so the bigger the gap, the more it's truly an ionic bond. So you can see when sulfur and oxygen get together, there's not a big enough gap there. When carbon and fluorine get together, it's a 1.4. It's not enough to make it ionic. It's covalent, and there's some more there that we got to cover about that, but it's covalent.
So the sodium chloride is the ionic.
It is ionic. And generally, one of the best things to think about is if you're mixing a halogen with an alkali metal, it's going to be ionic, especially higher on the list. Sometimes even when you're mixing a halogen with like a alkaline earth metal, the second column there, the calciums and that kind of thing, also ionic. Because you can see these numbers are very similar to this number, like calcium and potassium, very similar as far as their affinity for more electrons.
Not sure.
Yeah.
Did you say what the gap? I want to use it.
I think it's like 1.8, but you don't have to know that, and I don't even know it. Yeah, I just know it's around that, something like that. But that's how, like, when I took chemistry a long time ago, we had to identify as ionic or not, and you did the math, and if it was greater number, you called that. And I'm not even sure that that's like true science versus like a generalization. So you don't need to know it. Just the point is, the bigger the gap, the more likely it's ionic. All right. Let's take a break. Going by this clock, let's reconvene. I have to be out of here by 12:15 for a faculty meeting. Let's reconvene at 11:40. Okay? Because both parties are into that, they both have buy-in on the sharing of that 1 or 2 or sometimes 3 electrons. And so if it would take both of them to decide to let go for it to be dissolved. It's harder to divorce a covalent bond. All right. So they're strong bonds. You need to consider them the strongest bonds by far, the strongest bonds of any bond. And they can have either a nonpolar, which means like an unequal sharing of the electron, or an equal, or a polar, which would be an unequal sharing of a pair of electrons. Okay, so back to that electron negativity chart. See, I'm used to when I used to lecture in here, there was 2 whiteboards. Now I'm forced to be on one side. That's okay. I can deal. So we have carbon bonded to a carbon. Now carbon has 4 valence electrons, so carbon will only be happy if it shares 4 different electrons. It has 4, and the only reason why I know that is you look on the table, and you start from left to right, and you count 1, 2, 3, 4, you get to carbon. That means it has 4 valence electrons. It needs to be given 4, which it's not likely to be given because it doesn't have enough electron negativity, or to agree to share 4. So carbon actually needs to have 4 bonds. These dashes represent a sharing of 2 electrons. If I have 2 dashes, that's a sharing of 2 pair, or like 4 total electrons. So it needs to have 4. But when it's bonded to this other carbon, which is a very common bond, they both have the same value when it comes to that electron negativity chart I showed you. Which means this electron that is, these 2 electrons that are shared, there's an equal pull of those electrons. And we draw it this way, as what we call a sigma bond. And my drawing is very bad. I'm trying to show you that those are equal. And I know there's a little lopsided on the right there, okay? But these are equal. This means that there's an equal pull. This is called a non-polar bond. There's no poles here. There's no one side that's stronger than another, or one side that's more negative than another, or whatever, okay? Non-polar. But let's say here, this right here, we have a fluorine. Now, fluorine, if it was bonded to, let's say, sodium, it would be ionic. Fluorine would have taken sodium's ion and ran. It doesn't run, and that's another topic in a minute here. But it would have definitely taken it and kept it, right? But with another metal, it doesn't have enough electron negativity in comparison to the carbon to take it. It'll share it. However, it's going to be a hog. So it's not a bully, it's just a hog, all right? So in this bond, it'll look something like this. And I'm exaggerating here, okay? Where the electrons are shared, but they spend most of their time hanging around the fluorine. Because the fluorine is like, yeah, we'll share it. Yeah, sure. It'll be mostly mine, okay? All right? So what that means is these electrons will hang out in this region more than they hang out in this region. Electrons have a negative value. They actually have a negative charge. So where what it would have been neutral is going to be shared, but because those electrons hang out there too much, there's going to be a slightly negative charge over here. Let me say this. Fluorine, if I were to draw that valence electron dot structure, which there was a picture of it, there should be 8. There's only 7. So if it shares one equally with another one, it's kind of like, now it's 8. It's going to be negative, but it's going to be negative, but it's not going to be any more than the other side. But remember, they're sharing 2 here. So if both of them kind of spend more time over here than over here, this side is going to have a more negative charge than the other side. Polar bond, non-polar bond. Okay? So like I have these little stick figures. Purple, orange can represent halogen. I try to always use green for fluorine, orange for chlorine, and then if you see purple, it's usually like bromine or iodine. It's something else. You know? So these short sticks here represent the sharing of 2 electrons. It's that stick bond there. Okay. So we have a carbon here with 4 fluorines around it. We have another carbon here, why is it always hydrogen, where we have 3 hydrogens bonded and 1 fluorine bonded. So let's take this one for a minute. Each one of these, there's a sharing of electrons between the hydrogen and the carbon, hydrogen, carbon, hydrogen, carbon, fluorine, and carbon. If you go back to that chart for electron negativity, the value applied to hydrogen is much smaller than the value applied to fluorine. As a matter of fact, somebody go back and look. What is the electron negativity number for hydrogen? 2.2. What is it for carbon? 2.5. And what is it for fluorine?
3.9.
Okay. So let's talk about the 2.5 versus 2.2. 2.2, 2.5. That means that the carbon has a little bit stronger affinity for an electron than the hydrogen does. Okay? That means as it shares that electron, even though technically it's nonpolar and it's the same thing, when I talk about that 1.8, I think it is gap, if that gap is really small, we call it a nonpolar bond. Even though it's technically nonpolar, the carbons are going to actually kind of keep the electrons in a little bit more to itself than the hydrogen gets, because it's got more affinity for an electron than the hydrogen. It's opposite with the fluorine. The fluorine has 3.9 whatever, 9.8 or whatever. It's almost 4. It's way stronger than the carbon for the electrons. So there's going to be an affinity of electrons to hang out around this fluorine, which will then mean that this area is going to be relatively negative in charge, and these areas are going to be slightly positive in charge. So when you talk about the bond, although this one we consider nonpolar, this one will say slightly negative, and we use a sigma, like Greek alphabet sigma, slightly negative, slightly positive. So when you're dealing with a less complicated molecule like water, and you're dealing with that, you can easily ascribe that the oxygen, which has a much greater affinity for electrons than hydrogen, will have electrons kind of hanging out here more, creating a very slightly negative or heavy slightly negative negative side here and positive side here. So yes, polar bond, meaning there's that pull of electrons towards the oxygen, and polar molecule, because we got a couple things going on here. We got hydrogens with a slightly positive charge because they're giving the electron away more than they're taking it. We have oxygen pulling the electrons towards itself, and oxygen has 8. If it's in this state, it has 4, and sharing 2 and sharing another 2 from the carbon. Or more specifically, it started with 6, shares 2 of them. Where are the other 4? Well, we got the sharing 1 each here. Where are the other 4? They're hanging out over here. Why are they hanging out on this side? Because they don't want to be near those hydrogens that are kind of positive. Electrons are extremely negative. They're the epitome of negative, right? So we developed this, and that's, by the way, why it's not straight. The hydrogens kind of go by themselves over here. All the electrons and the pull of those shared electrons come over here, and we develop a very negative side here and a very positive side here. So this molecule is polar in general. That means that when it gets around another molecule, there are issues potentially developing where they might like each other more, or they might hate each other more being near them because there's more electrons on one side than another, or more negative charge on one side than another. So negative side here, are you videoing me?
I'm taking a picture, yeah.
And it's okay, I'm being videoed already, so I'm not offended, but I was just wondering, I thought you were chatting while I'm lecturing, So, okay. So, what do you think will happen when this water molecule gets near this water molecule? They'll kind of get near each other and they'll kind of go, hey, I like this. You think? No.
Not that side.
They ain't like, well, they like this.
Yeah.
They like this a lot.
Yeah. Hydrogen
Okay.
bonding.
And that's where hydrogen bonding comes in. Yes. So, now, is there polarity in this molecule? What is this?
It's O2.
Let's breathe it in. It's oxygen, right? Is there polarity in this molecule? Is there one part of this molecule that's got more electrons in general than another? Like, does this oxygen have more than this one? Or,
It should be
so this is
nonpolar.
not polar, okay? Which is crucial, and this is down the line, this is where all this comes into play, because if there was polarity, it would have a really hard time getting from your alveoli to your blood. So, thank goodness not, because if it was, we'd have a real problem living. So, back to these two. Electrons being pulled, electrons being pulled, electrons being pulled, electrons being pulled. Where on this whole big, like, let's make a sphere out of this, where are the electrons being pulled to what side? Like my right hand more, my left hand more? Not really. This molecule actually, because there's equal pull in all directions, this molecule is a non-polar molecule, a non-polar compound in space. Lots of polarity in the bonds, but not in the molecule. Take this one. Big pool of electrons here. A giving away of electrons here. Where's the polarity in this molecule? Here. Negative here and positive here. Polar molecule. Non-polar bonds, but the molecule is definitely polar. See the difference? The octet rule is just the whole thing referring to you need 8. Chemical bonding. Some gaseous elements exist as diatomic molecules. I definitely have to go faster. Like hydrogen gas, nitrogen gas, oxygen gas, fluorine gas. Don't breathe that very much. Chlorine gas, don't breathe that very much. All but nitrogen are quite reactive. So oxygen gas is actually quite reactive. Relatively speaking, it is. Hydrogen gas is extremely reactive. Put hydrogen gas and oxygen gas together and light a flame. Woo! Anybody ever see? That's where I was hooked, man. I was in the 6th grade. No, actually, it was 8th grade. We did that like. Anybody ever do that where you put you took a battery and you took like the 2 probes and you like made oxygen gas and hydrogen gas. You collect them in a bottle or a test tube. I see a couple nods. And then you took the test tube of hydrogen and you put the flame on it and it went. And then you took the oxygen and you put a flame to it and it went. Whoo. And then this professor took one of those old Coke bottles, like the small one, 6.5, like old 6.5 ounce ones, and he gathered both gases in it. So now we have equal hydrogen gas and oxygen gas. And we all had to stand back, and he held this thing out, and he took a flame, and it was like a shotgun. I mean, boom! And that was a massive, big reaction that occurred, and it was like, wow, that's so cool. I can't believe we just did that in school. I want to do that. Can I do that? It's probably illegal in school now. I don't know. Probably get fired for doing something like that now. What do you think was formed by the way? Hydrogen gas, oxygen gas, flame, explosion. What do you think the products were? Water. That's right. All right. Anyways, I digress. I told you I could go faster, and I'm digressing. Okay. All but nitrogen are quite reactive. So some equations of this reaction are shown the following way. You get 2 sodiums around. This 2 means it's a superscript. That means there's 2 elemental sodiums. They're not bonded together because it's in the front. All right. Bonded to a Cl2. When you have the subscript 2 behind it, that means you have 2 chlorines bonded together. Okay. And they form 2 NaCl's, table salt, sodium chloride. All right. You have 2 hydrogens, 2 oxygens. What I was just describing. So now you have. So this is 2 elemental hydrogens, which are diatomic hydrogens. So there's actually 4 hydrogens there. Okay. And 1 oxygen molecule to form 2 water molecules. Carbon with oxygen, CO2. Carbon with some fluorine, CF4, which I have that. I showed you that already. All right. Ionic bonding. So in the case of like these previous reactions, like take the sodium chloride one, this one. Sodium really wants to give away electrons. Chloride really wants to take it. So this is what happens. The sodium has 1 electron in that outer layer. It gives it away completely, 100%. It no longer has any tether to that electron. It is gone. It's away. Which means it has a full positive charge. Okay? Because the neutral charge that we have, let's say with hydrogen, for example, means that there's 1 electron to the 1 proton. They neutralize out, it's neutral. Hydrogen doesn't exist like that, by the way. Okay? But let's take sodium. How many people have ever held sodium in their hand? Anybody? Anybody? I mean, you eat it every day. You never held elemental sodium in your hand by itself? Just Na. I wouldn't suggest you do. Because elemental sodium is actually a metal. It's not bonded sodium, like sodium chloride or sodium acetate or sodium whatever that you're eating in your processed food. I don't have that much probably process it. But anyway, but elemental sodium is extremely reactive. I already told you, if it's in that first column, it's not happy. So elemental sodium, Na, is a metal, and you can just look up on video, on YouTube or whatever. Someone drops elemental sodium into water, and it's like super reactive. I mean, like fire and brimstone and all that. You know, okay? So that's sodium. Sodium is not happy by itself. Neither is chlorine. So you get them together, and sodium says, whew, here you go. Take my electron. It has a full positive charge. The chloride takes the electron. It only needed one. Now it can be like argon. It's happy now. Yay, I have one. But now it has a full negative charge. Well, then what happens? You got sodium sitting there with a positive charge, and chloride sitting there with a negative charge, and not only do they make each other happy, now they really like hanging around each other too. So they're attracted to each other because one's charged positive, one's charged negative, and they form an ionic bond, which is only a bond that occurs because they like being near each other. They're not sharing anything, and for lack of a better thing, they're like polygamists, but worse. You know, like they. I'm trying to. Shouldn't have gone there. Okay. Anyways, the point is they'll go from one to another, right? They're not married to any particular. That sodium, it may have given the electron to the chloride, but it might actually go get near a different chloride. It doesn't matter to that sodium that it was that chloride it gave the electron to. So the point is they can kind of shuffle around. And that happens every time in your water. If there's salt in there, that salt is floating away or floating around, and you have sodiums floating around, and you have chlorides floating around. They get around each other, and then they break away, and they get around each other. So it's not a very strong bond. Okay, it's a strong attraction, but it's not a bond that's very difficult to break. Okay, now, and so what ends up happening is they end up forming these ions. If they are positively charged, we call them cations. If they're negatively charged, we call them anions. And I use those terms a lot. Okay. So what do you mean cations? Is that like a I don't even know cats very well. I was trying to think of a particular kind. Oh, is that an ocelot? I don't know. Anyways, so cations is a positively charged ion. Anions are negatively charged. And then, so we have certain compounds that are very common. Sodium chloride is certainly one of them. Magnesium chloride, aluminum chloride, sodium oxide, magnesium oxide, etc. On and on and on. Okay, but these bonds in all of these are ionic bonds that can more easily be broken than any covalent bond. Okay. Now, the one caveat I have to that is if you get a bunch of ionic compounds around, or ions around each other, and then you dry them out, and they form a crystal, now they're kind of set where they are. So you could call this a strong bond. So when you have that table salt that you haven't dissolved in water in your cupboard, and you see that crystal of salt, it's going to be really hard to get that one sodium to move away from that one chloride. They're set. It's almost like they're concreted in. Okay. So yeah, that is a strong bond, but more because of the state of its phase than because of that strong bond. And this is a great picture that kind of shows that positive and negative aspect where the sodiums get real near each chlorides. Also, the lower on the elements, the bigger. So chloride is much bigger than sodium. So anyhow, this is also a great little thing to show. We'll get a lot into this when we do the diffusion mixture solutions lectures later this semester. But a solvent is like a liquid. A solvent can actually be a gas. It can be a lot of things, but we mostly think of them as liquids, like water, that things can dissolve in. Non-polar substances that don't have polarity, like lead, a bunch of carbons together, just a bunch of, I'm talking about like pencil lead, not lead. Anyways, a bunch of carbons together. Non-polar substances just don't like polar solvents like water. Water, I already explained why it's polar. And the reason why is because when it gets around these water molecules, it doesn't really have, it just doesn't like the chaos, right? It just wants something like benzene or something like that. But polar substances love them. This guy comes in here, fluoromethane. He comes in here near the water. He goes, ooh, I got this really negative side here, and oh yeah, that's good. I like that. And so it really likes getting in this mixture. Same thing with sodium chloride. You got all these sodiums and chlorides here, and once they're dissolved, once they kind of break up, they can go wherever they want. And so all the chlorides go and they hang around the hydrogens of the water, and all the sodiums go and hang around the oxygen side of the water. And this is why polar substances like to dissolve in polar solvents. Okay. Much more about that coming up in a couple weeks. Non-covalent bonds consist of, and so the main one we talk about is ionic bonds. Hydrogen bonds, we'll talk about in a minute. Hydrophobic interactions, London dispersion forces, like van der Waals forces, Keeson forces. As you go down the list, less and less important. Hydrogen bonds are important. There's a couple of examples where we see these. These are usually where you have a very strong, you have a covalent molecule with a strong polarity, a really strong polarity, like water. So this is showing water here, and I told you about that sigma, so slightly negative side here, slightly positive side here, a real focus of electrons over here, and then you have ammonia here, and when you have ammonia with these NH3s, you not only have this slightly negative side, but there's actually 2 electrons sitting up here as well. So really negative side here, and so there's quite a bit of bonding from one to the other. Not enough to share, not enough where it's giving away, but it's negative getting near positive, to the point where you almost form a pseudo bond, and that's called a hydrogen bond. And they do matter, and we'll talk about these hydrogen bonds off and on forever. One great example of a hydrogen bond is the bonds formed in the double helix. The amino acids that are between those. Hydrogen bonds being not so strong, they get near each other and form that hydrogen bond, and it can be ripped apart, not too difficult. Good thing, right? Because if you couldn't rip them apart so easily, thanks. You got what you got, no more. So, all right. London dispersion forces, formerly called van der Waals forces, are very weak interactions. They occur because there's even changes within the nucleus of where those those protons are primarily focused. It's very weak stuff. Okay. Keeson forces are formerly dipole-dipole interactions, right along the side of what we were talking about with hydrogen bonds. But the hydrogen bond is the main thing. Here's your double helix, your hydrogen bonds forming in between these amino acids. Before I go any further, I want to give you a list of molecules I expect you to know, or elements I expect you to know, and letters. Because I don't expect you to know cesium, but I do expect you to know hydrogen, helium. I wouldn't say like the top 30, but actually there's some I'll skip. Lithium. All of these, numbers 5 through 10, you can write that and write them out later. So really, actually 5 through 13. You could also say 1 through 13 minus 4. Beryllium we just never really deal with. Maybe that would be easier. All right.
1 through 13.
Minus number 4.
You said the letter.
So if I say B, you need to know it's boron. If I say boron, you need to know it's B.
Was there something else? So was it the letter and something else?
And then A. Yeah. So, and then you can skip 14. This is the rest of them. So you want to do that? Say 1 through 18 minus. You can even say 1 through 20. How about that? 1 through 20 minus 4, 14. Yeah, minus 4 and 14. Additionally, you need to know, well, I can tell you all of them, and then we go, yeah, 26, or write iron. First of all, I'll give you by name because it'll be easier than you'll have to go back and figure out. Copper, zinc, chromium, silver, actually I think you should know that, iodine, mercury, that's good. So, what is a mole? No? No? No, that's actually not my reference. Nobody? No. Austin Powers. All right. What is a mole? All right. Moni?
Yeah. He said, I'm in 3 in Goldfinger.
Oh, you know what? I didn't see that one so much. Where in that movie?
Anybody else? You did, yeah. Okay.
It was it was the mole guy?
Yeah.
Oh, which actually was in the third one, right? When he goes, mo, yeah, okay. Yeah, I guess I didn't see that one so much, so, yeah, okay, very good. Sorry, my bad. All right, so what is a mole? So, the bottom line, out of all of it, it's Avogadro's number. A mole is 6.022 times 10 to the 23rd, whatever. Atoms, molecules, elements, electrons, whatever, it's that number. Technically, it's the gram molecular weight of anything that we're talking about here. But really, it's Avogadro's number. So if I say you have 1 mole of carbon atoms, you have Avogadro's number of carbon atoms. But then you can figure out that therefore you have 12 grams of carbon atoms because you know the atomic mass of it. The number of moles may be determined by the following formula. Number of moles equals grams divided by the formula weight. So the formula weight for carbon is just simply C's weight, which is 12 grams per mole. So it'd be, if you had 12 grams of it and you divided it by the 12 grams per mole that carbon is, you would have 1 mole. Okay? The reason why we say formula weight is because most of the time we're talking about something that is a compound. So let's say we're talking about water. And I said you had 18 grams of water. How many moles of water do you have? Well, you would say, well, number of moles is equal to 18 divided by the formula weight of water, which is the molecular mass of oxygen, O, which is 16, plus the molecular mass of 2 hydrogens, which is another 2, 18. Right. You have 1 mole of water. Okay? Don't make you do a whole lot of that. And as far as molecular mass goes, I'm pretty sure there's none I expect you to memorize. I kind of think hydrogen's easy. So I don't know. Hydrogen, oxygen, and carbon. That's probably all I'd ever expect you to know. And I don't know that I ever asked you to do this calculation. But I might. So. But what if I did, and I didn't ask you one of those 3, or something else was in there, I would give it to you. I would say the molecular mass of nitrogen is 14 grams per mole. I'd at least tell you. Okay. Certainly don't think you need to go around memorizing that. Yeah.
Like it's okay if you say, 16, but not like 16.
Not in this class. We ain't worried about it, right? So okay, we're not chemists here. Okay. All right. So how many moles are in 23 grams of water? You say 23 divided by 18.015. You're really technical. I know I don't ask you to do that. So, all right. Polyatomic atoms. These are a special class of ions where there's actually multiple elements in that ion to then have its net charge. So some examples is like the ammonium ion, which has 4 hydrogens bonded to 1 nitrogen, and the net charge is a whole positive 1. Or nitrate, 1 nitrogen and 3 oxygen with a net charge of -1. Sulfate, hydroxide, like sodium hydroxide, like a pure base. Hydroxide is OH with a negative charge. You definitely will be dealing with that. Your hydrogen peroxide, there you go. Polyatomic, when compounds containing a polyatomic ion, they'll have a given name is used, like ammonium chloride. So whenever you take a halogen and you bind it with something, it's going to add the IDE to it. So chlorine becomes chloride. Fluorine becomes fluoride. Okay. So you have the name ammonium, and then the chlorine is now giving an electron away. How do we know the chlorine gave an electron? It's taking an electron. How do we know it's taking an electron? Because ammonium gave it to him. Or somebody gave it to him, sorry. At some point, the chloride gained the electron, has the negative charge, and then now ionically binds to the positively charged ammonium. That part I said is correct. So chemical bonding, I'm leaving in 5 minutes, by the way. Yeah. So a chemical bonding, we have all these. I'm going to tell you which ones you need to know the formula and name. Ammonium, all the plus ones. Okay. Acetate. Bicarbonate, also referred to there as hydrogen carbonate, but bicarbonate is by far the name that's commonly used, and you've got to know that one. You will see that one over and over and over again. Okay. Hydroxide, another big one to know. We're skipping a bunch. Yeah, I'm feeling phosphate. That's enough. All right, I'm afraid. Let me just see where we're at. Yeah, I can't do this in 2 minutes. So that's it. I'll have to finish up that last little bit, and then next week we'll do organic one. If you want, if there's one thing you can do to prepare by far the best with organic, is go ahead and familiarize yourself with all the functional groups and their structures. You know, I have quick examples for you here. Things like, what does an aromatic look like? We have here an amide, an ester, a ketone, things like that. An amine.
So you'd want us to draw them?
What's that?
You would want us to draw them?
You will need to be able to do that.
Yeah.
I mean, not necessarily in class next week, or by the exam you will, or the quiz. But I'm just saying, if you can really start familiarizing yourself, and so I'm not taking so much time explaining that this is a carboxylic acid and why is it a carboxylic acid, or that this is an ether here, and that this, by the way, anybody can tell me what this is? More common name? You will give this to a lot of patients. See both? So, all right. All right. Very good. 1, 2, like, that was me. When I did all my shadowing, we never talked anesthesia. Ever. Like, nobody I shadowed ever talked a bit about anesthesia with me. I just watched them do stuff. I got into school and I had no idea what C4 is. If that's you, yes, it's okay.